Okay, I think we can get started. Tracy, do you want to start the recording?
Hold on just a sec, Katie.
Yeah, no rush. Okay, great, thanks. Welcome everyone. I'm really happy to introduce our seminar speaker today, Dr. Danielle Touma. Dr. Touma is a postdoctoral scholar in the Bren School of Environmental Science and Management at the University of California, Santa Barbara. She received her bachelor's and master's in civil engineering from North Carolina State University and her PhD in Earth System Science from Stanford University in 2018. During her PhD, she received an Outstanding Student Paper Award from AGU and a Mentoring Award from Stanford in 2017. She joined UC Santa Barbara in 2019 and is also currently a visiting researcher at UNCAR working with folks in M-Cubed. Danielle's research focuses on understanding the impact of climate variability and human activity on the characteristics of extreme climate events. She's currently investigating the role of anthropogenic activities on fire risk, quantifying the risk of post-fire extreme precipitation, and assessing the spatiotemporal connectivity of extreme climate events. Today, she will speak about anthropogenically driven increases in extreme fire weather conditions and subsequent extreme precipitation events. Danielle, the floor is yours.
Awesome. Thank you so much for having me and for that introduction. So I will share my presentation. Hi, so does that screen look good to everyone?
Looks great.
Great. So yeah, so thanks for having me. I'm excited to share my work, or our work, looking at increases in extreme fire weather and subsequent extreme rainfall events. Oops. So this work is largely motivated by the recent unprecedented wildfire activity we've seen across the globe. There are many examples of this, but I'll focus on a couple. This is an image from the recent Western US fire season, which lasted around 6 months and I believe is currently restarting. So it's not a great time to be out here in terms of wildfire. But these recent fires burnt over 10 million acres across Washington, Oregon, California, and Colorado. And around half of that area was in California. And this unprecedented fire season is actually part of a much longer trend that we've been seeing here in California. This figure here shows the area burned in California from 1950 to 1920. And you can see that this figure at the time, this figure hasn't really been updated with the final numbers, which is around 4.4 million, I believe. But you can see that from 1950 to 2020, and even before 2020, there's been an ongoing increasing trend in the area burned in California. And this most recent year really doubled or more than doubled that the previous record that was set in 2018. And these wildfires caused large impact on communities, on the environment. There were 46 deaths across the Western US, and there's also been a new study estimating that there's an additional 3,000 deaths due to the poor air quality, either already occurred or will occur in the future. So really drastic impact. And these impacts have also been trending in the recent past. This recent paper by Marshall Burke and co-authors at Stanford estimated the percentage of PM 2.5, that's particulate matter 2.5, that can cause a lot of respiratory issues. They they've estimated that the total amount of that comes from wildfire smoke has increased in the last 13 years or so. The different lines are showing estimates from different models, and they all agree that there's this long-term trend. They also agree on this really large spike in 2018, which at the time was one of the most severe fire seasons recorded in the Western US. So these kind of impacts are increasing, have been increasing in the recent past. In other parts of the world, there's also been trending towards more intense and larger fires. This is an image from the Siberian peatlands, which have been burning over the last 2 years. The most recent fire season out there started in May 2020, and I'm not really sure if it's still ongoing, but the last I checked, they still were. And at the time, they had burned over 140,000 square kilometers. And one of the trends they've been seeing there is an increase in fire intensity. So here I'm showing a figure that has an estimate of fire intensity for a given day in August. And you can see that the gray bars here show the 2003 to 2018 average. That's the record that they have. But you can see that the 2019 values in yellow and 2020 values in red are much, much higher than those of the previously recorded average. So this is another trend that we've been seeing in different parts of the globe. And these wildfires also have detrimental effects. They're releasing many, many megatons of CO2 and causing a lot of poor air quality across the EU. Another impact that wildfires have are that they can create suitable preconditions for debris flows and flash floods. So this image on the left is from the 2018 mudslides that occurred in Montecito. These mudslides occurred because around 1 month after the Touma fire, which was the largest fire at the time in 2017, there was a really intense storm that occurred over Montecito and over the burn scar. And due to the conditions that the wildfire created on the surface there was a really hard to predict and intense debris flow that occurred, and sudden debris flow that occurred. And this led to 23 deaths and many homes destroyed, as well as many buildings and infrastructure. And this Montecito is just a few miles from where I live now. And if you go out there, you can still see them rebuilding and recovering. So it's been quite a severe impact there. This is not just unique to California. This also happens in other places, such as in Colorado. This image is from the 2013 flash floods in Manitou Springs, Colorado. And these flash floods occurred when severe thunderstorms, when there were severe thunderstorms over the burn scar of the Waldo Canyon fire. These thunderstorms occurred 1 year after the fire in 2013 and caused 4 flash floods over the summer. And in 2015, which was 3 years after the fire, another flash flood occurred when another thunderstorm was hit the burn scar of the Waldo Canyon fire. So these wildfires can create preconditions, not only for 1 year, but these preconditions can last up to 5 to 10 years, which some studies have shown when it comes for debris flows or flash floods to occur when there's a severe storm. So in this talk will be a two-parter. In the first one, we'll try to understand the drivers of these increases in extreme fire weather across the globe, specifically greenhouse gases and aerosol emissions. And in the second part of the talk, we'll look at how elevated extreme fire weather conditions could possibly lead to more impacts from extreme rainfall events occurring over the Western US because of the preconditioning of wildfires. So this first part of the talk is based on a recently published paper and was co-authored by my advisor, Sam Stevenson, Flavio Lehner, who's now at Cornell, and Sloan Coates, who's at the University of Hawaii. So for a fire to occur, we need three main factors. We need an ignition source. This can be human caused or natural, such as lightning. We need resources to burn, so vegetation on the ground. And we need suitable fire weather conditions. These are dry, warm, windy conditions that help ignite and spread a fire. And we as humans have been changing all three of these things. We've been developing wildland-urban interfaces. They're known as WUIs here. I don't know if that's what they're known in Colorado too, but we've been developing those. And so by having more homes and infrastructure out in these wildland areas, we're increasing the probability of ignition just by humans interacting with forested areas. And also our infrastructure has been aging, and this causes more chances for ignition if there's a down power line or a failed transformer. We've also been modifying the resources or the vegetation we have to burn through development or through fire suppression. There's a really great literature base on fire suppression and how that's contributing to increases in wildfire area and intensity. And the last piece of the puzzle are these fire weather conditions, and this is what I'll focus on in this talk. So through anthropogenic climate change, we've been changing temperatures, precipitation patterns, relative humidity, and wind. And through these, by doing so, we've been altering the frequency of extreme fire weather conditions. So there's been a lot of evidence showing that drier fuels lead to larger fires, and drier fuels can become more frequent if we have more drier conditions, atmospheric conditions. So this figure from Abadzoglu and Williams shows this relationship quite well. They show a really strong relationship between fuel aridity and forest fire area on a given year. You can see, and another thing they show is that more recent years, which are in red, have had drier fuels and larger forest areas. Similarly, in Siberia, this figure here shows that there's a strong correlation between moisture availability and burned area in Siberia. So that's kind of these locations in red that are stippled. And this is also has been shown in the most recent fires where the fuels are quite dry right now out there, so contributing to the intensity and area of the fires. And Abadzoglu and Williams in the same paper showed that these dry fuels are really driven by anthropogenic climate change. So here they're showing a time series of burned area on a given year in the Western US. And they show that, and red is the observed time series. So with observed climate conditions. And they show that you can't really model or simulate these observed forest fire areas when you don't include anthropogenic climate change. That's the line that you can see in the gray. And you really have to add the anthropogenic climate change contribution to be able to get to the observed conditions. So by adding the black and yellow lines, you can get to the observed conditions, but you can't actually get it without anthropogenic climate change. And Williams et al. Go on to show that anthropogenic climate change going into the future will permanently elevate fire weather conditions by 2050. So here this map shows that around 60% of the global burnable area will have kind of a new normal of elevated fire weather conditions by 2050. And this is very stark in the Amazon and parts of Africa as well as Europe. So we wanted to understand what is really driving these different, what is driving extreme fire weather and the trends in extreme fire weather in terms of the different components of anthropogenic climate change. And we wanted to do this because we know that anthropogenic forcing effects vary in both space and time. This figure here is taken from Clara Desser's paper, recent paper looking at the different effects of anthropogenic forcing on different climate variables. And here I'm showing the surface temperature trend for 1970 to 2019 for aerosols on the left and greenhouse gases on the right. And you can see that there's many regional differences in terms of aerosol forcing, as well as regional differences in greenhouse gas forcing. So you can see that while greenhouse gases do elevate temperatures almost everywhere, the regional there's a strong regional pattern. And if we look even earlier in time, back to from 1930 to 1979, you can see that both the patterns and magnitude of these effects have changed over time. So there was a much stronger cooling pattern back in due to aerosols back in from 1930 to 1979. And the warming pattern for greenhouse gases was much lower than it was in 1970 to 2019. So we wanted to consider these different regional impacts on the climate and understand what that means for extreme fire weather. And we also know that anthropogenic forcing effects are also subject to climate variability. So here I'm showing temperature anomalies, global temperature anomalies from 1920 to 2020 from the same study. And you can see that there is still in ensembles, there's still quite a bit of climate variability when we're looking at the effects of these different anthropogenic forcings, where the aerosols are in blue, greenhouse gas effects are in red, and the fully forced simulation is in black. So you can see that there's quite a range in when looking at any of these forcings. So we also wanted to be able to capture that. So to do so, we tapped into this great resource that's at NCAR, led by Jen Kay as well as Clara Desser. And these are the CESM large ensemble experiments. We have an all forcing experiment, which is one that you might all know already. And this experiment is forced by both historic forcings from 1920 to 2005 and future forcings from 2005 to actually goes to 2100 using RCP 8.5. And I'm using the first 35 members, and the members are all separated by small temperature perturbations, which are set in 1920. And so this allows us to capture the climate variability as well as the forced response in this all forcing ensemble. We also have some I call them sister experiments or accompanying experiments, but these are all but one forcing experiments. In terms of the climate variability and the perturbations are kind of set up in the same way. But in this case, the all but aerosol forcings have fixed aerosols from 1920 onwards, as well as greenhouse gases, biomass burning and land use change. They all have fixed forcings, depending on which one it is, from 1920 onwards. The all by aerosols and all by greenhouse gas experiments have 20 members each, and they go up to 2080, while the all by biomass burning and all by land use change have slightly smaller ensembles and only go up to 2029. So in this talk, I'll mostly be focusing on aerosols and greenhouse gases, mostly due to the ensemble size, as well as the length of the simulations. And we quantify extreme fire weather using the Canadian Forest Fire Weather Index. This is very similar to kind of the forest fire danger rating that's used in the US and that Smokey the Bear likes to use. And this Forest Fire Weather Index accounts for maximum temperature, precipitation, relative humidity, and wind on seasonal to daily scales. And this allows us to understand or quantify what the fire weather conditions are on a given day and how likely it is for a fire to ignite and spread. And to really capture the days when fires could be large and severe, we use the 95th percentile of the fire weather index, which means that around 5% of days in a given year in the historic period will have extreme fire weather for a given location. So to understand what the regional expression of anthropogenic activity on extreme fire weather is, we use the risk ratio. And this risk ratio is used in attribution studies quite frequently. And so the way this risk ratio is calculated in our study is by dividing the probability of having extreme fire weather with a given forcing by the probability of having extreme fire weather without that forcing. So that means that if the risk ratio is greater than 1, that forcing has increased the risk. And if the risk ratio is less than 1, that forcing has decreased the risk. So here I'm showing a map of the risk ratio for aerosol emissions for the period we're currently in, 2006 to 2029. You can see that the risk ratio of extreme fire weather is reduced in many parts of the globe due to aerosol emissions, especially over the Amazon, parts of Europe, parts of Africa. However, the aerosol emissions do increase extreme fire weather conditions in some locations, such as Southeast Asia, Western North America, and parts of Eastern North America. On the other hand, greenhouse gases generally increase extreme fire weather risk across the globe. So here you can see, but here you can also see that there are regional differences. For example, in the Amazon and parts of Europe and Asia, there's the risk of extreme fire weather has almost doubled due to greenhouse gas emissions, while in parts of parts of North America, Australia, and parts of Africa, that risk has increased by around 20 to 50%. So there are some strong regional differences. And so to understand these regional differences and how they change through time, I'm going to focus on Western North America and the Amazon, just because they look so different and we live in Western North America. So here I'm showing the risk ratio under aerosol emissions for Western North America. So we were around here in the map. And I'm also showing the ensemble spread. So kind of the effect of climate variability on this, on the effect of aerosols on extreme fire weather. So you can see that in the 70s, all the way to 2000, the aerosols reduced extreme fire weather risk. But going into the future, the aerosols slightly increase extreme fire weather risk. When we overlay greenhouse gases on top of this in red, we see that greenhouse gases continuously increase extreme fire weather risk all the way from around the 60s to the future to 2080. And by 2080, extreme fire weather risk has increased by around 60 to 70%. If we look at the Amazon, we see a much different story, especially in magnitude. We see that extreme fire weather risk will continue to increase under greenhouse gas emissions all the way up to 2080. If you really squint your eyes, you can see that that aerosol, on the other hand, aerosol emissions keep reducing extreme fire weather risk well into 2040. However, this is really much smaller than the effects that greenhouse gases are having on extreme fire weather risk. So we kind of wanted to disentangle these a little bit more and understand why greenhouse gas forcings would have such different effects in different regions. We found that the changes in maximum temperature, specifically increases in maximum temperature, tend to increase extreme fire weather risk similarly in both locations. However, we found that there are projected slight increases in precipitation under greenhouse gas forcings in Western North America, which tend to dampen the increases in extreme fire weather risk that would otherwise occur. And we also found that in the Amazon, we see a reduction in precipitation, and this increases extreme fire weather risk further. And we see increases in wind, which also increases extreme fire weather further. So these increases in temperature, decreases in precipitation, and increases in wind compound to really increase extreme fire weather risk in the Amazon, according to these simulations. We also wanted to understand how these different effects, anthropogenic forcing effects, influence this time of new normal, which I showed earlier in the introduction. Here I'm showing our own version of that, looking at the time of emergence in the all forcing ensemble using CESM. And we find similarly that extreme fire weather risk will become the new norm, has already become the new normal in some places, such as the Amazon, parts of Europe, parts of Africa, and that it will become the new normal by 2080 in around, I believe it was around 75% of the globe. But we wanted to take advantage of these all but one forcing simulations and understand why we are getting to this point. So we found that when we look at the all but aerosol forcing ensemble, we find that aerosols generally delay the time of new normal by a couple of decades in some places, such as the Amazon region and parts of Europe. On the other hand, they do accelerate the time of new normal by a little bit in some other places, such as Australia and Western North America and Northern Europe. When we tried to do the same thing for greenhouse gases, we found that we actually couldn't calculate a number in most of the globe because we actually did not see an emergence of extreme fire weather in the all but greenhouse gas forcing experiments. So that means that permanent emergence of extreme fire weather only occurred when we do include greenhouse gas forcing, and actually does not occur without it. So this is a really interesting finding for us, and it was fun to try to make this map as well, all stippled. So, so I'll do some takeaways for this part of the talk. We found that greenhouse gases increase the risk of extreme fire weather in the recent past, and they will continue to do so in the future under the RCP 8.5 forcing scenario. And we also found that while aerosols reduced extreme fire weather in the recent past, that effect will diminish in the future, or even reverse in the future slightly. So we wanted to ask in the next part of the talk is, will these heightened extreme fire weather conditions increase the impacts of post-fire extreme rainfall? So is it more likely to get rainfall events that could cause debris flows or flash floods, given that we have more days of extreme fire weather and possibly fire events? So the study is in collaboration with, again, my advisor, Sam Stevenson, as well as Danielle Swain, Deepti Singh, Dmitry Kalashnikov, and Xingying Wang. So we do believe that we should expect an increase in kind of post-fire extreme rainfall due to some studies that came out recently. So this paper by Danielle Swain et al. Showed that the frequency of dry to wet years is projected to increase in the future in California. So here you can see that there's around a 50% chance of having this kind of what they call a whiplash event, going from an extremely dry year to an extremely wet year in parts of California. And then another paper recently found that the same year burned area and precipitation intensity is expected to increase under the same RCP 8.5 forcing. So areas in red here in California show regions where this compound hazard, having a large burnt area with high precipitation intensity, is expected to increase everywhere that's red here in California. So we wanted to look at this in the CESM large ensemble, and here I'm only using the all forcing ensemble. And because we have such a large ensemble size, we're able to kind of detect these type of events, these very rare events, because we have so many simulations, and we can analyze all of these events in kind of a statistically robust way due to this large ensemble. So when we zoom into the Western US, we find that the frequency of extreme fire weather events, and here I'm using a slightly higher threshold to really capture those events that could lead to large fires, the 99th percentile. You can see that there's a robust increase in extreme fire weather events compared to this historic period, 1980 to 2005. And by 2100, there's around a 200 to 300% increase in extreme fire weather frequency in parts of the Western US. We also find that the frequency of extreme rainfall events, and here I'm using the 99.9th percentile for rainfall, also increases in the future. Actually, I didn't really need to plot the negative part of this, this bar, since there's mostly increases in the frequency of extreme rainfall events over the Western US. And again, parts of the Western US show around 200 to 300% change in extreme rainfall events frequency. So to understand a little bit more about what's going on, I'll focus a little bit on California and Colorado to understand how they differ and what we should expect in terms of post-fire extreme rainfall. So here again, I'm showing the frequency of extreme precipitation events on the y-axis and the change in the number of extreme fire weather events on the x-axis. And each point here represents a different ensemble, and each color going from the lightest to darkest represents a different period in time. So you can see that early on in Colorado, there's quite a large spread in both the change in extreme precipitation events and the change in extreme fire weather events. However, it seems like the change in extreme precipitation events is a little more robust in terms of positive changes than the change in extreme fire weather events in the early period. In the later period, there's still quite a spread, but most of the ensemble members are showing increases in both extreme fire weather events and extreme precipitation events. Oh, and you can see the PDFs here for each variable as well. You can see the same kind of findings. And so, yeah, here we're showing that there's, but we do see that there's still quite a large spread, especially in the later period of extreme rainfall and extreme fire weather frequency, going both in the X and the Y axes. On the other hand, California shows a little more robust changes, especially in extreme fire weather events. You can see that early on, most of the ensembles do show an increase in extreme fire weather events. However, there's still a little bit of a spread in extreme precipitation events across the ensemble. And so we find, that there are more robust increases, especially in the later future period in extreme fire weather events. However, there's still a large spread when we look at the extreme rainfall events. So we wanted to understand what these changes in annual frequency meant for the timing of getting extreme rainfall after an extreme fire weather event. So here I'm showing the likelihood of having an extreme rainfall event 1 year after an extreme fire weather event. So here we're sequencing the events where we need to have an extreme fire weather event, followed by an extreme rainfall event within 365 days after that event. So here we see that in the historic period, the likelihood of having this type of compound event is 10 to 20% in many parts of the Western US. Going into the future, we see that that likelihood increases. By 2100, parts of the Western US show that it's more likely than not to have an extreme rainfall event occurring after an extreme fire weather event. So these are the kind of, these point to increases in the chances of debris flows and flash floods. Right, but in many parts of the and even in locations where that kind of 50% threshold isn't reached, we still see large increases. For example, Western Colorado goes from a chance of around 5 to 10% to closer to 50%, so large increases there. And so again, we'll zoom into Colorado a little bit. I think it's an interesting place to look at these kind of events. So to better understand kind of when these rainfall events are occurring, I've plotted the monthly number of these extreme rainfall events that occur within 1 year of an extreme fire weather event. And for each month, you can see 3 bars. These represents different time periods, and they're showing the change in the frequency, the annual frequency of these extreme rainfall events occurring after an extreme fire weather event. So, and this is the annual frequency for all of Colorado. And this is the average of the ensemble. So you can see that there's generally increases. The increases get larger as we go further in time, and there's increases throughout the year. We wanted to understand really how impactful could these events be. So we subsetted these events to find rainfall events that occur within 6 months after an extreme fire weather event. So here we find that especially for the late summer and fall months, a large portion of these compounding events are occurring within 6 months after an extreme fire weather event. So these kind of events can be a lot more impactful in terms of debris flows and flash floods. And we wanted to further understand kind of the risks of these events. And so we looked at those that occur within 3 months or less of an extreme fire weather event. And we found that especially for the summer months, around half of those compounding events occur within 3 months. And in the fall, around a third of those events occur within 3 months. And we found that this is mostly due to the kind of the seasonality and the changes of extreme fire weather events and extreme precipitation events. So we found that in Colorado, there's a large increase in extreme fire weather events in the summer, as well as a large increase in extreme precipitation events in the early fall. So this causes an increase in both these 3 month and 1 month, 3 month and 6 month events. If we look at California, it looks much different. The first thing we notice is that really the increases in these type of events only occur during the historically rainy season of California. And that very few of these events increases in events are these 3 month events. And most of them are these 6 month events, especially in the early winter and in the winter. And again, this is due to the seasonality of the changes in both extreme fire weather events and extreme precipitation events. And we find that there are also increases in extreme fire weather events in the summer in California, just as they were in Colorado. But the increase in precipitation events only really start occurring in the early winter and not in the early fall. So that means that there's many more 6 month events and not 3 month events. So I'll stop here for this part of the talk. So we found that there are robust increases in extreme fire weather events. And these extreme fire weather events do occur earlier and drive the earlier increases in the compounding rainfall events in many parts of the Western US. And there are later increases in extreme rainfall events, and these tend to accelerate the increases in the likelihood of these compounding rainfall events. And what this tells us is that there's really a really heightened potential for debris flows and flash floods that could occur in the future. And they do vary across seasons and regions as well. Again, I just want to remind everyone that we are looking at extreme fire weather events and not specifically fire events. So there's still a little bit of a modeling gap that we need to fill there, but it really starts to show us that, it's something we do need to look at. So yeah, so I'll stop there and take any questions. Thank you.
Thanks so much, Danielle, for that really nice, really nice talk. It's really obviously a really important topic to us in Colorado, as well as you in California. So I'm sure it's on a lot of folks' minds. So we have plenty of time for questions. As always, if you have questions, you can type them in the chat or use the Zoom raise hand feature. Let's start with a question from Isla.
Hi, thanks. Nice talk. mentioned, changes in the real world at the beginning. I was just wondering if you kind of done a more detailed comparison of the model with what's actually happened, since some of these signals seem like we should be seeing them already, at least for the first part. Are there places where the model is definitely doing things wrong and we can tell that already, or?
I actually haven't looked at kind of the signals. I've looked at more like historical averages, and the models do tend to do a decent job in terms of spatial patterns. They don't always get the magnitudes right, like for extreme fire weather. They don't get like that threshold value right. It's a little underestimated, but trying to think what we've done. Yeah, so we haven't actually looked at these, especially for the second part of the study. We've started to look at some extreme rainfall events occurring on kind of observed fire scars, but we're still trying to understand what that means.
Yeah, I can imagine for the precipitation part, it would be difficult in the real world, but for like the Amazon, it seemed like the signal is already there now outside of the noise.
Yeah, I know that there's some work that showed that maybe the Amazon is not, in terms of extreme fire weather, there's some issues with maybe the wind or relative humidity out there. So maybe we are overestimating them, but I'm not sure. If we look at just maximum temperature, we still see a strong signal there. So if we kind of ignore precipitation and relative humidity, there's still quite a strong signal compared to the rest of the globe. Yeah. So if we do trust maximum temperature, which I think we can at this point. So
yeah. Okay, thanks.
Thanks.
Linda, go ahead.
Myself. Danielle, really nice talk. Thank you very much. I'm wondering about the robustness of your results, particularly about the extreme rainfall events and the wildfire risks, in terms of other global models versus the variability across the ensemble members. So I think you indicated that there was actually a precipitation increase, I think, for a number of the ensemble members. So was there much variability? For example, were there, other ensemble members where there were real decreases in precipitation? I'm thinking about the Western US. Just do you have a feel for how the variability across the ensemble members compares with the variability across, the various CMIP models?
Yeah, that's a really good question. We found quite a large variability for the coastal California, especially for fire weather. And we think that's because the winds on the coastal California aren't well simulated, especially offshore winds. So it's, I think, mostly depending on temperature and precip changes, and precip is, there's large variability in precipitation changes out there as well. And we did, in terms of California as well, we found that there's another study led by Michael Goss that showed increases in extreme fire weather events in the fall when using, I believe, like some other CMIP5 models. And so we didn't see that in CESM lens. We actually saw some very slight decreases in extreme fire weather in California in the fall. So we definitely need to take that into account, and it might be interesting to do kind of the same study on other large ensembles, or just the CMIP5 or CMIP6 models to kind of understand where its CESM lies in terms of the full distribution, especially for these very extreme events.
Yeah. Great, thanks very much.
Thank
Question
you.
from Laura, go ahead.
Hi, Danielle, thank you. I wanted to double check my understanding, and this is changes in extreme fire weather, so it doesn't take into account fuel loads. So for example, changes in
Exactly.
forest management that might change fuel loads. So it's assuming that the amount of fuel available is the same and then just looking at the weather impact, right?
Exactly. Yeah, we're just trying to focus on kind of the meteorological conditions, and we're not really assuming whether a fire occurs or not. We're just kind of trying to find times when the meteorological conditions would be suitable for a large fire, or a severe fire, if other things came into play as well, such as ignition and fuel load.
Okay, thank you.
Yeah, thanks, Laura.
So there's a question that came in the chat from Richard. I also see Richard's turned his camera on. Would you like to ask your question out loud?
Okay, sure. Can you hear me?
Yeah.
Okay. I was interested in knowing if you switched the order that you're searching for relation. Did you look at the relation between extreme precipitation events 1 year before an extreme fire event? There are a number of reasons to do that.
Yeah, so kind of like perhaps reducing the chance of having an extreme fire weather event. Is that kind of what you're thinking about?
Well, no, there are a number of possibilities. One of them could reflect on the question that was just asked. If you got a lot of rain year before, that might reduce some of the fuel, but also if you're just getting a whole lot of precipitation every year, then you would get more the year before and more the year after. So there are a number of reasons to look at that. I just wondered if you did.
Yeah, we haven't actually looked at it in this study. I am looking at it a little bit in the project that Katie mentioned I'm on as well at MQ, but we haven't really found anything. I haven't really done the analysis properly yet. So, but yeah, it's definitely something to think about. And yeah, kind of like if we're getting more and more extreme rainfall events every year, does that make a difference than getting it like just after extreme fire weather events? No, that's a really good question, and something to think about maybe for this paper or the next one. So
nice talk. Thank you.
Okay, Clara is next. Go ahead.
Yeah, thanks, Danielle. I had a related question, I think, to Richard's, but maybe phrase it a bit differently. So your second take-home message here, the title of that paper, are you implying a causal link between the summer wildfire conditions and the risk of the extreme rainfall events? Or are you really just saying, because extreme rainfall events, at least I'm familiar with the Colorado setting, I think would tend to occur more in the early autumn, that seasonal phasing is just, as you said, that's really why there's that delay, but it's not intended to be a causal link. So if you had looked at just extreme summer temperatures, would you find that same then risk for extreme rainfall events in the autumn? Do you see what I'm trying to say? So are you implying some kind of memory via the land surface to the rainfall after a wildfire risk condition? Or is it just, because of the seasonal cycle?
I'm implying more the latter, more of the seasonal cycle. I definitely see that this title could, maybe we should change it because it does imply a little bit of causality now that I read it with your viewpoint in mind. But That's something we're not doing. We haven't done yet, but that's something I am interested in doing in the future to see, does, for some reason, the conditions that cause extreme fire weather events kind of lead to conditions that cause extreme rainfall events. Is there some sort of connection there in terms of atmospheric dynamics or land surface conditions? So that's, a really good question, but I'm not implying causality in this case.
Yeah, I didn't think you were, but I think one has to be very careful.
Yes.
How you frame it.
Exactly. Okay. Definitely, this is a working title, so I appreciate the feedback. So
that's great. Thank you.
Okay, question from Rohini. Go ahead.
Thanks, Daniela. That was super interesting talks, both looking at things. And my thinking was exactly going what the Clara also said, and Richard, like what would be the physical mechanism that you would provide for such a linkage? Of course, statistically we can prove, because one variable can increase in the future with respect to the contemporary condition. So how do we disentangle the role of natural variability versus the warming effects that we would see? I mean, like, did you try with somehow like disentangling the warming effect from these runs?
We actually haven't. That would be something. I'm wondering how we could disentangle the warming effect from. I guess we could do kind of a thermodynamic versus dynamic comparison in terms of the precipitation, changes in extreme precipitation, and we could possibly remove the thermodynamic effect. But I actually haven't done that or thought of it, but that's, so.
One way was, which I thought that Richard was pointing out, and if I'm not, if I'm wrong, please correct me, that when you change the sequence, then you know that by chance, how much time you get that other kind of events.
Yeah.
So statistically, but still it's
yeah, so that's something we could do, like bootstrap, and so we can change the kind of the sequencing of the events, the daily events, and try to understand is it a warming signal, or is it kind of the day-to-day variability or seasonal variability.
But one thing would be very much clear, that if you are like in working or preparation of this paper, it would be like that you are not trying to give the indication towards casuality, rather looking at the conditions, because more people tend to think like, yeah, this is coming, there is certain linkage in that too.
Exactly.
And that is what you don't want to give it.
For sure, yeah. Definitely don't want to give causality if that's not what I'm analyzing, so.
Great.
Thanks for your feedback.
Yeah, excellent discussion. In the last minute, I'm just curious, Danielle, if you have any thoughts about one of the last points you mentioned, which is closing the gap between modeling extreme fire weather versus actually fire events, because I think that's of interest to this group, is sort of what we need to do to close that gap, or what are the limitations, or if you have any thoughts on that topic.
Yeah, I think one thing I'm excited to do in the next couple of years or so is to look at the new CESM has better kind of wildfire modeling capabilities than CESM1 did. So I'm hoping to kind of use the new use simulations from that model to look at these again, but maybe use actual fire area burned versus extreme fire weather events, since those simulations will account for things like ignition and fuel loads as well. So it will allow us to really understand these kind of risks going into the future. But I also believe that just knowing that there are these kind of two extreme events occurring within a short time period, you know, between each other is also important, because these can have impacts anyway, even if there's no actual fire. It could lead to multiple evacuations or kind of, you know, thinning resources. So even if there isn't that debris flow or flash flood, there still could be some large effects separately from each other. So that's also something we're trying to look at in this work.
Awesome. Thanks so much, Danielle, for a really nice talk. Thanks everybody for the questions. Next week, we're going to have Tom Buechler from UC Irvine and Columbia present at the seminar. So hope to see you then. And thank